All right, future astrophysicists, welcome. Today, we are going to get into one of the most fundamental questions in all of astronomy. How in the world do we measure the universe? I mean, how do we figure out the distance to things that are just incomprehensibly far away? It's a huge challenge, but it's the foundation for pretty much everything we know about the cosmos. So, let's break it down.
I mean, this is the big one, right? It's the question people have been asking forever. Just by looking up at the night sky, it seems totally infinite, maybe even unknowable. But you know, in science, we don't just stop at wondering, we measure. So the real question is, how do we possibly put a number on something so gigantic?
Yeah, you can't exactly take a tape measure and stretch it out to the nearest galaxy. The scales we're talking about are so massive, they completely break our everyday brains. When you look at a picture like this, what you're really seeing is an enormous, profound measurement problem.
To solve it, astronomers came up with this really elegant and ingenious strategy. See, you can't make one single jump to the edge of the universe. So instead, we build a ladder. It's called the cosmic distance ladder. And the idea is that each method, or rung, lets us reach a little bit further out. And each rung helps us calibrate the next one up. So here's our game plan for the climb. First, we're going to tackle the first rung, parallax. It's our only direct measurement. Then, we'll reach out even farther with something called standard candles, which are like cosmic lighthouses. After that, we take the final leap with redshift, which lets us map the expansion of the whole universe. Then, we'll check out the view from the top and wrap up with a quick quiz. Let's go.
Okay, first up is the absolute foundation of this entire ladder, stellar parallax. This is so important because it is the only direct geometric way we have to measure how far away a star is. Everything else we're going to talk about is built on top of this one technique.
And you know what? The concept is actually really simple. Go ahead and try this with me. Hold your thumb out at arm's length. Now close your left eye and look at it. Now switch and close your right eye. See how your thumb appears to jump back and forth against the background? That's parallax. Astronomers do the exact same thing, but our eyes are the Earth on opposite sides of the sun. We look at a nearby star, wait 6 months, and then look at it again. The star will seem to have shifted just a tiny bit against the backdrop of much more distant stars.
And this diagram shows you exactly how that works. What we've got is a giant triangle in space. We know the length of one side of that triangle, the baseline, because it's the diameter of Earth's orbit. And by measuring that tiny angle of the star's shift, we can figure out the other angles. Once you have a baseline and all the angles, boom! Simple trigonometry gives you the distance to the star. It's just pure, beautiful geometry. Now, the big challenge here is that these angular shifts we're trying to measure are unbelievably small, like ridiculously tiny. And from down here on the ground, our own atmosphere blurs and jiggles the starlight, which makes getting a precise measurement super difficult. This is exactly why space telescopes like Hubble are such a total game changer. Getting up above the atmosphere means they can measure these tiny shifts with incredible precision, which lets us push this parallax method out to thousands of light years. It makes the foundation of our ladder strong.
Okay, time to climb to the next rung. Parallax is fantastic for our cosmic neighborhood, but it only gets us so far. To measure the distance to whole other galaxies, we need something different, an indirect method. We need to find standard candles, objects that can act like lighthouses in the cosmic darkness.
So what exactly is a standard candle? Well, imagine you see a single light bulb way off in the distance. If I told you that you knew it was a 100-watt bulb, you know its true intrinsic brightness, you could figure out exactly how far away it is just by seeing how dim it looks, right? A standard candle is just the cosmic version of that. It's any object where we know its true brightness, its absolute magnitude. We measure how bright it appears from Earth, do a little math, and we can calculate its distance. And our first, and one of our most important, standard candles was discovered by the absolutely brilliant astronomer Henrietta Leavitt back in the early 1900s. She was studying these pulsating stars called Cepheid variables, and she noticed something amazing. There was a clear, direct relationship between how long it took for the star to pulse, its period, and how bright it actually was. All of a sudden, by just timing the pulses, we could know its true luminosity. It was a massive breakthrough that turned these stars into perfect cosmic yardsticks. Now, Cepheids are great, they really are, but to see across the truly mind-boggling distances to faraway galaxies, we need something even brighter, a lot brighter. And for that, we turn to one of the most spectacular and violent events in the entire universe, a Type 1a supernova. These are not just any old star explosions. A Type 1a supernova happens in a very specific way. You have a small, super-dense star called a white dwarf,
and it's in a binary system, stealing gas from its companion star. It just keeps pulling in more and more mass until it hits a very specific, critical limit, about 1.44 times the mass of our Sun. And at that exact moment, it triggers a runaway thermonuclear explosion. And because they all go off at the same mass, their peak brightness is incredibly consistent. They are almost perfect standard candles, and they are so bright we can see them clear across the universe, billions of light years away. Okay, now for the final rung on our ladder. This is the big one. It lets us measure the universe on the largest possible scales. For the most distant objects out there, we're not even looking at individual stars anymore. Instead, we are literally measuring the expansion of space itself.
Back in the 1920s, Edwin Hubble was looking at the light from distant galaxies. And when you break that light down into its rainbow of colors, its spectrum, you see these dark lines. They're called absorption lines, and they act like atomic fingerprints, telling you what elements are in that galaxy. Well, Hubble noticed that for distant galaxies, these fingerprints were all shifted over toward the red end of the spectrum. He had this incredible insight that this red shift was happening because space itself was expanding, literally stretching the light waves as they traveled across the universe to reach us.
And this led to his monumental discovery, what we now call Hubble's law. He found a direct, straight-line correlation. The more red-shifted a galaxy's light was, the faster it was moving away from us, and the farther away it had to be. This was huge. It gave us an incredibly powerful new ruler. Now we can just measure the redshift of a galaxy, and from that, we can figure out its distance. This is how we map the universe on the grandest of scales. So, we've climbed all the rungs. We've gone from parallax to standard candles to redshift. What have we actually learned? What does our universe even look like when you put it all together? What's the view from the top of the ladder? And here it is. This is the stunning result of all that work. Now, this isn't an artist's drawing or a simulation. This is a real map based on data. Every single point of light you see is an entire galaxy, and its position was plotted using its redshift. And what you see immediately is that galaxies are not just scattered around randomly. No, they're organized into this vast, beautiful, interconnected structure of filaments and clusters with huge empty voids in between. We call it the cosmic web. This is the largest scale of our universe, all revealed by climbing that ladder. And just to keep our sense of scale in check, it's always good to remember the incredible variety of stars we're actually measuring. They range from tiny, dim red dwarfs, which can be just a fraction of our Sun's mass, all the way up to these colossal blue supergiants that can be over 150 times more massive. And it's the specific life cycles of these stars, especially the violent deaths of the ones that create white dwarfs and supernova, that give us the standard candles we need to build this incredible cosmic map.
All right, you made the climb with me. So now it's time for a quick pop quiz to make sure everything's stuck. Let's see what you remember from our trip up the cosmic distance ladder. First question, what is the one and only direct geometric method we have for measuring the distance to stars? You got it? It's stellar parallax. That's the bedrock, the foundation for everything else. Question 2. Who was the amazing astronomer who discovered that critical relationship for Cepheid variable stars, the one between their pulsation period and their brightness? That was the brilliant Henrietta Leavitt. Her work gave us our first great standard candle. And for the final question, when we say the light from a distant galaxy is redshifted, what does that actually mean? It means that galaxy is moving away from us because the universe is expanding, and that expansion has stretched the light waves, shifting them toward the red end of the spectrum. So we did it. We climbed the ladder and we mapped the visible universe. But I want to leave you with a final thought. All of this structure, this entire cosmic web, is really just the visible stuff. Astronomers believe the vast majority of the matter that's holding it all together is something called dark matter, something we can't see at all. So the next great challenge, the next ladder we have to build, is figuring this out. How do you map the invisible? But that's a question for another time.